this round is, it's called Understanding Dual Fuel, but not to disappoint you, the beginning of it has to have a foundation of heat pumps and knowing how heat pumps work before you can start building on dual fuel. So they're really connected together, and the start of this is really going to be understanding what I would say lessons learned and things important to me to understand when you're looking at a heat pump system. Things that if you overlook, they'll give you grief as long as you try to go back out and continue to work on them. So the goal is to give you some insight of those things so that as you go out and start working in the field, or if you have, and maybe some of you are experienced heat pump specialists here, don't raise your hand, you'll embarrass me because you probably got more on this than I do. Questions are welcome at any time. Raise your hand, shout them out. You don't have to wait to the end. There'll be an opportunity at the end as well, but I like interaction as much as any of you have the question. We'll take it on the fly. The agenda for today, we're going to go over really the basic operation of heat pumps, and then parts and pieces that make the difference, parts and pieces that we need to understand so that when we get to the dual fuel piece of it, it all meshes and that second stage equipment of whatever that looks like will function properly. Refrigerant storage and accumulator, the necessity of a match system, I'll hammer that point home very hard. Crankcase heater requirements, coil placement, second stage operation, how that all functions, how that all works together with, especially with a dual fuel. And then the defrost cycle, the backup heat, how those function in with, and again, this is heat pump stuff. This is stuff you can take with what I call single fuel, electric heat pump and electric resistance heat. The dual of the fuel is just simply because you got natural gas or propane or fuel oil or something like that, which back in the day we did a long time ago. And then determining where to set that balance point so that your homeowner doesn't get cold or the system just runs nonstop without keeping up. So those are our points that we want to hit today, and we'll have a cover slide for each one. Basic heat pump operations we're going to start, and it's pretty much the basics. It's understanding, and I went and looked at a lot of different diagrams out there online. Half of them miss the accumulator, and half of them are not realizing the value and the importance of that accumulator. This is AC. On the AC side of things, is the accumulator necessary? Not as much, because a system that is designed for a specific tonnage or capacity will require more refrigerant in the cooling load, in the cooling load than in the heating load. Less refrigerant in the heating load, and I'll explain why as we go through these two. And that's one of the things that makes a difference in matching the system and also in the system functioning and operating properly. The simple basics here, I'll just touch on them. The coil releases the heat in the condenser, and in the indoor coil, which we call the evaporator, it absorbs that heat. And I don't know that I'm going to go through, hopefully everybody understands the basic refrigeration cycle from this point. The only other thing is we do have a reversing valve. Two things to point out with the reversing valve. One, the hot gas always goes in the side of the reversing valve that's a single port on this case on the top, and the side that's going to the suction of the compressor always comes out the middle of the 3-port side. A simple way to remember as you're looking at heat pumps and working on them, those are 2 ports that are always consistent, and it's just simply the outside 2 ports that is what is going to make the difference whether it's heating or cooling. The second slide here is basically the opposite of what we just showed you, where the coil inside gets hot, it releases the heat, and the coil outside absorbs the heat. And that heat that it's absorbing is sometimes not very much. So it's taking a lot of that coil space to be able to absorb that heat to actually boil that refrigerant off to be able to get it in a vapor form back to the compressor. What happens if there's some liquid that goes back through there? That's where the accumulator comes in. The accumulator is an additional device, or I don't know what the better word, a canister really. A can is what it is. And if you was to look inside it, you would actually see a tube that goes all the way to the bottom and then comes back up most of the way. And in the bottom, there's holes in it, small enough so that as oil comes back through to get back to the compressor, it starts filling up the bottom of this canister. Those holes allow that oil to go in at the bottom and to be drawn with the vapor, with the tube going almost to the top, all the liquid settling to the bottom of the accumulator, the vapors at the top. It's pulling the vapors off the top down past that oil, seeping in those holes and carrying that oil to lubricate the compressor and get back to the compressor. So a couple of important pieces there. One, that's needed in the heating cycle versus the cooling. And our next slides will kind of highlight that, and that is just simply understanding that refrigerant storage and the accumulator, how that all works. Where does liquid go in the refrigeration cycle? Where does it reside? And we know we'll start in the outdoor unit, hot gas condenses to liquid in the cool mode. That's what we're used to. And the point I want to drive with this is there is a distinct physical difference in the size of the coils of the indoor and the outdoor. And so when you're in the cool mode, you have all sorts of storage space outside for that liquid that's condensed to sit and to be held. All of a sudden, when you swap things, now in the heat mode, this is your storage container. And it's a fraction of the size, a lot of times, of what that outdoor unit is. So what do you do with this extra refrigerant? It's got to go somewhere. And if you're not sized correctly, what can happen is if you don't have enough storage space for the liquid in the evaporator or the indoor unit, I like to tell stories of real life occurrences here, and going back a few years, and I went to my distributor and I bought a matched set from the distributor. It was a air handler with a coil and a condenser. Put it in, and springtime, charged it up, everything was working great. It was dialed right in. We got to the fall, went out, and it was kicked out on high head pressure. Put my gauges on, and I ended up pulling like 1.5 pounds refrigerant out of it. Good bit. And it worked fine all winter. And next spring, when it started getting hot, the homeowner called and said, AC's not cooling. Went out, it's like, well, does it have a leak? It lost some charge. Added 1.5 pounds of refrigerant in it, and it worked beautiful all summer long. That fall, another call. No heat. High limit tripped. I did that, unfortunately, embarrassingly, for 3 years. And the third year, I went back to the distributor and said, there's something not right here. They matched up the system. They says, we know you bought that from us. Who was the counter person that sold that to you? Because for the 5-ton unit, that should have had a second stacked coil on the outside of that air handler with a tube to connect the two to pull from 2 coils, basically to give you enough storage area in the wintertime for that extra refrigerant, because there was no room for the extra refrigerant in the wintertime. And I was having to pull it out and put it back in. And the happy ending is they replaced the whole system for me because that coil was no longer available. But that's the lessons learned, and that's why it's so critical on the heat pump side of things. Another story, microchannel. Everybody familiar with microchannel? Some people use it. It's still out there, I think, some today. Microchannel condensers are so flat. There's so limited amount of storage in there, even in the AC only side of things, that 2 ounces of charge will make a difference. 2 ounces overcharged or undercharged in the system. 2 ounces undercharged, and it won't cool. 2 ounces overcharged, and you'll be blowing fuses. And so storage capacity in heat pumps, of being able to store that liquid, and the value of that accumulator is extremely valuable for that heat pump to run and to operate. Uh, and I think we've already went through this. Really, the purpose of that is to store that extra refrigerant, to be able to hold that extra capacity designed by the manufacturer when they designed the indoor coil, the outdoor coil, and the size of that accumulator. And so all three of those things are designed together when they design these systems. And to be able to put a system in, and I'm going to go ahead and jump to it because I can talk to it here as well. One of the fears that I fear in what we heard yesterday of the 2026 heat pump revolt that potentially could be coming is homeowners saying, I don't want to replace my furnace and coil, just give me a new condenser. Well, all we can get you is a heat pump condenser. That's fine, just put it in, it'll cool, right? Yeah. And so they start putting, oh, by the way, you said it's a heat pump. Could you hook that up too? And now you have two different brands of products that are completely incompatible with each other. You may get lucky and have them work, but more than likely you're going to end up pulling charge and adding charge like I did. Yes, question.
Any reason you can't just install a receiver somewhere in the line set so we're trying to get it?
So you can install a receiver or a larger accumulator, but what's your efficiency? What are you doing for that homeowner efficient-wise with two systems that aren't even design rated? You potentially could be given an 8 SEER or a 10 SEER at best. That and I mean that's the worst case scenario. Really, or maybe I should say the best case scenario because the compressor size, everything is designed to work as a set, and if you're trying to fix something with patching it, yeah, we'll get to that. I jumped the gun here a little bit. Necessity of a match system. Here you go. This is my favorite one right here. It runs. It's I think at least a half a dozen different manufacturers of cars that they pieced this Corvette together, and it runs. But how well does it run? How efficient does it run? And if you're in a wreck, what body shop's going to take it to be able to fix what parts and where are they going to get them? Why does it need to match? And here's, you're not getting it off to a good start if you got a Linux unit inside and you just go ahead and put a Bryant unit on the outside. Now, there is one thing to keep in mind with this, and you'll notice that on this, it is a downflow. So the coil is on the outside outlet side, and we're going to get to talking about that in a little bit. But when a homeowner is looking to save money on the replacement, they're not looking to spend it on their energy bill for the next 5, 10, 15 years. And so matching those systems, getting the indoor and outdoors is absolutely necessary to make the system function and work right. What needs to be together? Indoor coil, outdoor coil, accumulator, they all need to match. And here's what you're going after. Adequate refrigerant storage capacity. You don't have issues with pulling Freon and replacing it. Sorry, I say Freon. It's refrigerant, I know. That's another story. We'll skip that one for now. Maximum heat output capacity, minimum energy consumption, and the homeowner comfort. All those things are compromised when you don't match that system up together. That's the first step in getting a dual fuel system installed properly, is having the heat pump system match properly. If you have issues here and you're going with dual fuel, you're going to have a layer on top of a layer trying to figure out what the issue is, where the problem is, and that could make it more difficult trying to diagnose. Here's your source of truth for systems, AHRI directory.org, and I actually went through and screenshot how to get all the way from residential to heat pumps to AHR ratings. That is where you're going to find all of your data for every system that's matched. If you're pulling permits for your jobs, I know in California, these are a required document to submit with it to show that the system has been properly matched and that you're getting the efficiency that you want to. We'll get to another slide a little bit later on that this website is extremely valuable for as well when you're setting that system up. But there's times that I would go in this and a little, if you're doing searches, a little tip here is you can put asterisks or stars, put the first couple letters of a model number and put a star, and it'll bring up everything of that first part model number. So if you don't know your sizes, if you don't know your 24, 36, or if it's a 37 you're looking for, or something like that, you can actually put an asterisk there, and it'll pull all of the options up with those letters. And then you can, or maybe it has a dash and you don't realize it has a dash. It's like, how come I'm not finding anything? Put a star. That dash can show up. Oh, there's a dash here, and then you can see some of the numbers and kind of get your way of going on, and maybe use a star again to be able to get the rest of that. So when you're trying to match things up, that asterisk is your friend to be able to get through there and find exactly what you're looking for. Correct. So the comment here is you can, if you have your load calculation, you can search by your BTU capacity, your rating or your load that you have that you're looking to accomplish that way as well. So there's times that I would be searching a specific load for maybe the cooling. California, that's a little more critical. And then seeing what all my options were for matching up what furnaces would go with that to see which furnace I wanted. And I would have that list of all of the compatible equipment that would match up with that. So great source of information here. If you don't use it, I would highly recommend it. This is kind of a side note, but I threw this here in the middle because of the criticalness of this. Do you have to add a crankcase heater? No. About everything comes with one today. Is it working? Have you checked it? Do you check it when you do maintenance? Do you have your techs go out and put their amp meter and clamp it on the lead to make sure that you do have a small amount of amperage being pulled through this when it's running? Be a good idea, especially on heat pumps. And if you're running dual fuel and you're going to get additional heat in by that indoor coil, we'll go through that a little bit here with this of why that's valuable. Air conditioning has little concern for crankcase heaters, with the exception if you're in an attic somewhere and that attic's super hot. And we're dealing with refrigerant or refrigeration mitigation. What is that? Well, that's when if you have one area inside or outside that's warmer, when refrigerant gets warmer, it vaporizes, it boils, and boils that off, and it moves. So as that vapor moves, it ends up back at the compressor. If the compressor's cold and you have that vapor that's back there, mixes with the oil, and then when it goes to start, your oil can be mixed with that vapor, and it's not going to give the proper lubrication for the compressor. You go another step further, and you can end up with liquid filling the compressor. And that liquid, you go to start a compressor with liquid in it, then, because the other spot's warmer, it's vaporized everything. It's now sitting vapor, empty, and all that liquid's moved to where it was colder. And you're slugging a compressor when you're starting it up. Worst case scenario. I don't know that I've seen a lot of that. Jeff back here in the audience is shaking his head. Yes, he has. It's out there. So is it a concern? No. If you're in an attic, if you're in a basement, it's not a problem. If you're in an attic where it's 100+ degrees in the summertime for the AC, and that it's hotter up there than it is outside, then yeah, you need a crankcase heater on a straight AC. It's the heat pumps that's the risk, and especially when they're off in the wintertime when it's colder outside than inside, where that liquid's going to build up outside in that condenser and compressor. So a little bit about crankcase heaters. Where do you put them? Well, I actually saw one put right on the top once, and I wasn't sure who they sent out to do that. But ideally, you're close to the bottom. You're within a couple inches of the bottom. That's where the oil is going to reside. That's where you want to keep that oil warm, as well as the base of the compressor, so that you have that refrigerant vaporizing and not sitting in that area in liquid form. What are you looking to draw? Somewhere about 0.1 to 0.3 amps is what your average crankcase heater is going to pull. So if you don't have that as a part of your regular maintenance program, especially for heat pumps, I would recommend that you add this for any heat pump PMs that you're doing out there in the field. One more piece on wiring a crankcase heater, and that just simply is, there's a couple thoughts on how a crankcase heater is wired. Some will wire them so that they are on 24/7, that they get power from basically L1 and L2, or on the slide here, 11 and 23. And then they rely on the thermostat to open up when it gets warm enough at the crankcase heater. The ideal place to wire these is on each side of the contact points, so that when the compressor stops, when the contact points open up, you're now getting 110 on one side coming from L1, and you're back feeding through the circuit of the compressor back to terminal 21 on the other side, and that's getting your complete circuit to get that crankcase heater heated and functioning. Once the contacts close, that whole line is now L1, and two wires on L1 have no resistance. You're not going to have a heater functioning when it's running. So by wiring it on each side of the set of contacts on a contactor, it's on when the compressor's off, and it's off when the compressor's on. And it saves that compressor, or that crankcase heater, from being on when the compressor's making its own heat. Question?
Does it make any difference if I wired on, up there you got 11 and 21 versus 23 and 23? I've noticed before on two-pole contactors maybe that I don't seem to draw current always when I'm wired the way it shows.
If you're on a 2-point contactor, you won't. If it's got to be a shunt. That shunt has to be able to carry that one side back around when it's off. If not, you're not going to get the circuit, and at that point in time, you need to be on 11 and 23 on a 2-pole contactor. Yeah. 90% of the contactors out there, everything that's being made today is a one, we call them 1.5 poles with the one side shunt. So that is recommendation on crankcase heaters and the importance they are needed to be in there if you're running a heat pump, especially if you're working on dual fuel. This is now getting more into the actual coil placement of how do you hook up a coil or install a coil for a heat pump if you have a gas furnace involved as well. Where do manufacturers put the coils? In air handlers. And you'll find every air handler that the coil will be upstream from the blower and the electric resistance heat. And there's a reason for that. If the heat pump is running, you don't want additional heat being added to that coil, the heat pump coil. And here's why. If you got a gas furnace, your temperature rises 40 to 70 degrees. So if you're pushing 70 degrees into the furnace and you're raising it a minimum of 40 degrees, now the air coming out of the furnace is now 130 degrees instead of 70 degrees. And if the coil is after that, you've just increased the coil temperature 40 degrees and the coil pressure. And what you'll end up doing is increasing the high pressure on the heat pump to either take out the compressor if it doesn't have a high limit, or trip the high limit. And so the placement of a coil when you're doing dual fuel, if you want to run them both at the same time, the coil has to be just like air handler manufacturers are doing, upstream before the fan, before that second stage of heat. That way you are not overheating and or should we say superheating the refrigerant in that coil as it's going through there. So importance of the placement of the coil. Yeah, I could tell you a story about that, of one that we put on the other side and kept wondering why we were tripping the limit, and ended up having to take the coil and move it around to the other side of the furnace so that eliminated that. And everything worked beautifully once we got it to the right side. It would look like this right here. These are terrible pictures. I'm sorry, I couldn't get good pictures of these. And I'm not crediting any installation. Mm-hmm. You're pulling through, just like you would an air handler. So if your indoor coil is installed before the second source of heat, you can run them together. If you leave your coil on top of on your exit side of your furnace, you're either going to run your heat pump or your furnace, one or the other. You're not going to run them together. Or if you try to run them together, you're going to run the risk of either blowing a fuse, eventually taking out a compressor, or kicking out the high limits.
What would be the advantage of, the picture on the left? What would be the advantage of being able to run your heat pump and your gas at the same time?
It's your auxiliary heat. So if you don't do that, when you go into defrost mode, what are you going to do?
Well, and that's another question I had too. Is when you go to defrost, I guess I did have that general question.
Yeah.
And I got a dual fuel. I go to defrost. My indoor fan never starts, and so what? I just theoretically have a 15, 20 second ignition sequence before I produce any heat back in the air.
On dual fuel, yes, correct. You're going to have to correct, and that's all determined by your thermostat. If your thermostat is thinking it's heating, that fan never shuts off, because the defrost board isn't telling the question was, I'm sorry, I should repeat the question, on using dual fuel. If you're using the gas furnace and the fan goes off during the defrost mode, and the fan typically won't go off during the defrost mode is the answer. The fan is predicated upon the thermostat thinking it's in a call for heat. It doesn't realize. So
the fan stays on, right?
Correct.
The heat pump goes into defrost. It sends a call in W to the furnace. The fan's staying on.
Correct.
It's call for W, so it goes for ignition sequence.
Correct.
10, 15, 20 seconds.
Correct.
Ignition.
Correct.
And then you've got fire. So you've
Correct.
got a short period of time where you're blowing
cooler air. So there is a period of time that you would blow cool air with the dual fuel system. There is a period of time before your electric resistance heat is building up temperature to be able to add heat to that. It's going to be a lot less, but it depends also on how much of your resistance heat. If you have 10 kW and you're only using 5 for your defrost, you're still going to be barely tempered with that. If you're pushing everything for your defrost electric heat strips as you would for W2, then you would have that, yes. Comment? Correct. Yeah, I've not seen the limit pop on that with the amount of time that it would take to switch with the two of them. So yeah, and a valid point. If your heat pump's running and you're kicking on your gas furnace, do you run that risk of running out on a limit? However, keep in mind that if your gas furnace is coming on second stage, your heat pump and fan are already running. So you're actually starting to cool that heat exchanger as soon as there's fire in it. You aren't building up temperature in that heat exchanger prior to the fan coming on. The fan's running through the whole cycle.
I wonder As we're going more heat pumps and more dual fuel, would OEMs be able to start putting some logic in the defrost board that might send a call to W 15 seconds before it actually sends the heat pump to the defrost? That way, the moment it goes to defrost, I've got my ignition sequence on. I think the only way that the board knows to go to defrost is when that sensor opens. There is no like defrost anticipator.
Correct. Correct. So the comment, and I'll repeat it here. The comment is, it would be the logic in the defrost board that would be able to know that it's going to check for defrost. The challenge with that is, depending if you're time defrost or demand defrost. If you're time defrost, then you can push that timer in there. If you're demand defrost, then it's going to check, and if it doesn't need defrost, it's going to pass and can continue to run. And so
defrost, it waits 15 seconds, and then it sends a call to the W, waits 15 seconds.
Correct.
Once it hits, send a call to W, delay my defrost. Yeah.
Correct.
Yeah, I don't think we could do that. I don't think we could do that.
Yeah. Question online?
My question online was these are the main issue you see with the coil before the furnace. The coil makes so much more moisture, it corrodes the furnace boards that aren't as protected the way they are in an air handler. And do you have any way to mitigate that?
Yeah.
So the question is, or the comment is, there's additional moisture that you're dealing with at the furnace board whenever you're dealing with the coil being before. That the only mitigation that I would be aware of with that would be simply being able to make sure that you're regulating your CFM of your blower accordingly for the humidity level in the region you're in. And if you look in every installation manual that's out there from what I call the big 7 manufacturers, you don't just simply say, these are your speeds at 400 CFM. You'll find ranges from 300 CFM all the way to 450 CFM in every manufacturer's installation instructions, giving you that liberty, that license to adjust that CFM for the amount of humidity you have for the area you're in. And example of that, like we're here in Florida, we're running 350 CFM predominantly on every install. That's what it's going in at. If you're in Colorado, there's a good chance you could be running 450 CFM on every job because it's dry. You have no humidity to take out. So the faster you run, the more efficient you are, and you can gain efficiency by running it faster. And so my only comment online would just simply be to make sure that you are adjusting your CFM, your airflow in that system to match that, and that would be the best course of action that I am aware of. If you have that level of humidity, I'll put a little piece in here for Nikki out here, Nikki Kruger at Santa Fe Dehumidifiers. You may want to invest in something like that to help with the humidity level as well. So comment here in the back of the room.
You said the biggest thing that maybe would make sure that it's for that application. But the other thing you've done in the past is actually put so much dirt. You got a sheet of 5, 6 inches maybe tall to make sure that if there's, because I've been on jobs where you've had the sheet on one, is it the splash, you get the sheet on the road, and then just as a safeguard. That's all, because usually when you go out of oil,
Yeah. Thank you. 2 great comments. One, make sure that you're matching your indoor coil to your load so that you are able to get that humidity out. 2, have your shop fabricate a little splash guard that's coming up and covering that control so that you don't have moisture hitting it as it's going through. So thank you. Shouldn't. The moisture around it shouldn't be any different than the moisture around in your supply ductwork. And if you have mold growing in your supply ductwork because you got extra moisture, then you have another type of issue. Yeah, and you shouldn't have that much moisture at that control that would cause that issue. I've not seen it. If anybody has, Jim Fultz at copeland.com, and you can look at the YouTube whenever they get it up, and get my email again if you want. And send me a note, because I'd be curious to know what you've experienced with moisture with this. Great discussion. Thank you. I was thinking I was going to get done early, so you've kept me on track. Appreciate it. Let's hit the defrost cycle and the backup heat a little bit here while we're at it. Again, that secondary heat can only occur if the dual fuel has the in dual fuel, if that coil is before the heat. And the benefit of that during defrost, you can now turn on that additional heat in defrost. By the way, don't look at these installs. They're pretty awful. I'm going to go on to the next slide here. He introduced me as Jim from Copeland White Rogers, and lest I get fired, this is a part of our installation instructions from our 47 DO1 universal defrost control, which we'll have one slide on that towards the end. I'd rather teach you and try to help explain what you can learn in the industry and understand that we do have some solutions, and we will get to them. Defrost function, when the defrost initiates, and we've already discussed this, I'm preaching to the choir here, I think. It's the energize of the auxiliary signal going out from the defrost control that allows that dual fuel or that second stage to be able to kick in. And there's two things within our universal board, and most boards, or at least some boards, you should be able to do this. One, auxiliary heat lockout or dual fuel lockout, where you can actually set in the control that the second stage or the dual fuel will not come on until it gets down to a certain temperature, and you can set that at wherever you want. In ours, you can set it anywhere from 0 up to 40 degrees, or turn that feature off. Low temperature cutoff would be what we would use when we're dealing with a balance point, and that's our next and final section here, that we're going to talk about what that balance point is and how that's set. But the secondary heat, this is the opportunity to say, okay, we're going to use the heat pump at its maximum efficiency. If you're not in a super humid area and you're not going to be going through defrost until it gets colder, then being able to set this at 40 or 30, where the second stage doesn't kick on, maybe not 30, 35 to 40. I know our numbers are going down and down as we get to cold climate heat pumps, and it's pretty exciting to see what we can do with that. And we are set up with these in the low temperature compressor lock cutout. We can go down to -10 before the compressor is locked out.
So we're using cold climate heat pumps exclusively,
Mm-hmm.
and they're not cut off at any temperature.
Great. So this little feature right here, OF, it's missing the second F. You can turn it off. Yeah, absolutely. Yes, absolutely. So that's how you use your backup heat balance point. A couple different things with balance point. How do you know what that balance point is? Is it something because the homeowner's uncomfortable, or your dual fuel, if you set it up, the primary heat pump will operate till it calls heat satisfied, or it drops below this determined point? And so if you don't set that point, then you have a second stage or a secondary heat, then your thermostat, unless you have a special intellectual property thermostat that's going to switch over and allow the second stage to heat until it's satisfied. Most of the time, your second stage will kick on after the first stage hasn't been able to keep up, and it'll drop out before it's at full temperature. So you can have your heat pump basically running 24/7, which is fine if it's creating comfort for the homeowner and it's not drafty for them. If it's drafty for them, then you may want to consider a balance point at which you do shut that second stage or that primary off and make the second stage the first stage.
Great picture, by the way.
Thank you. They're not very happy with the air coming out. So yeah, it's just uncomfortable coming out of there. So ba- balance point. And what is the balance point? And there's a couple different balance points, and I'm only touching on one of them. There's a second one that I'd encourage you to do a little research if you're curious about. This one is the balance point of capacity, what that heat pump can do. And one of the things that you're looking at when you're sizing things is, I think we heard yesterday, if you size it for the heat capacity and you're way oversized for your cooling capacity, then you're going to have moisture issues within that system, because your cooling capacity is dropping the temperature before it's pulling the humidity out. Your latent's not getting out. And so when you size that, you look at, and these are the three, actually there's four things that you need to know for the capacity side of things. One is, what's the heating load of the house? The 99% of the design temperature. And that on this, we're going to call A. That's the design temperature of the capacity that we need. And B and C are two numbers, heating capacity of heat pump at 17 and 47. Where do you get those numbers? Those are coming from this ahridirectory.org. You can go in there, find your match system. It's the other benefit of having a match system. You actually get numbers that you can find for a balance point. If you're mixing things together, you have no idea what these numbers are. And B is at 17 degrees, what your capacity is. C is at 47 degrees. You draw your lines, and D is where that balance point, where the heat pump capacity will not keep up, and where the load is greater than that, and that's at the point D, which is right a little over 25, 26 degrees. So for the balance point of this system, if you set for the compressor, the outdoor unit, to shut off, and the dual fuel or the inside heat to take over as first stage, you could set it at 26, and you'd maintain the temperature that you want in that house at all times. Or you could be a little bit comfortable, give a little cushion, and maybe set it at 30 degrees. Most of the time, I think 35, 45 is usually the range of most balance points that are set out there. But they can go lower than that and function just fine. So here's our two solutions. One is in a thermostat, and one is in a control. If you have a control in your system that you like and that you're using fine as far as the defrost control, then a feature that we just released this summer is built into the thermostat. The thermostat's connected to Wi-Fi. It gets open weather data, so it's going to be the temperature of your region, of your local town, where it's pulling that data up from. And within the settings, you can set it to heat pump, 1 stage, 2 stage. You can add your gas furnace or your electric heat resistance heat if you're not doing dual fuel. And it gives you the ability of that balance point setting. It's factory default at 80 degrees. It's factory default so that it won't kick out on a balance point. You have to push it down to somewhere between 40 to 30 or wherever you want that balance point to be. So it's designed, if you happen to get in there, that it's not going out and the homeowner's like, wait a minute, something's not on and it should be. But that feature is built in there where the thermostat actually switches and makes that second stage or the second fuel as the primary fuel, anything below the temperature that's being read by open weather. The 40D 01U, our universal defrost board, a couple plugs for that. One, it has the option of demand or time defrost. So if you're out on a heat pump that has a time defrost in it, and the homeowner's getting a defrost every 30 minutes, you have the ability to upgrade that board in that control to our defrost board and program it to go demand, so that they're not going into defrost every half an hour and wasting all that energy for the defrost. And the upgrade to that board will cover itself for the homeowner's savings in short order with being able to go to that. Yes. Those these have harnesses that plug onto them, and they just have short pigtails with spade connectors on them. So you just take the spade connector off your old and plug it right in. So it's yeah, there's no crimping, no wire nuts, just plug and play. And it also does read the low voltage. If it drops, I believe, below 18 volts, it's comparing that to a high voltage brownout. So it does have brownout protection on it as well through the low voltage side of things. So the smiley face is on there. Absolutely. We still have the smiley face on there. We also have it so you can mount any direction. And then the first thing you go into setup is you change the orientation of the smiley face. So it's always looking right at you. And the universal controls there, the last of our line here. If you're in gas furnace area, we have a whole bunch of universal controls, anywhere from our first one here that covers 550 different SKUs. No harnesses anymore. It's plug and play directly into the harness from the furnace. We have a universal igniter, or excuse me, flame sensor that has taken off. Yeah, thumbs up. Thank you. You can bend it, you can cut it, you can make it match any other flame sensor out there, and it's got a great review on it as well for Universal. So lots of really cool things happening with White Rogers. Questions? Yes.
I have a question about airflow in a dual fuel system.
Yes.
Would you want a different airflow in heating with the furnace than you would say cooling with the heat pump? And how does that change?
That is a great question. What's the airflow in heating versus cooling with dual fuel? And with dual fuel, your airflow is always determined by the airflow the coil is required to have to function properly. In other words, you're not going to slow your fan down to be able to pull more heat off a heat exchanger in dual fuel. That fan will continue to run at the rate designed for the heat pump for your 350, 450, whatever range you are for CFM. What does that do to the furnace as far as being able to get as much heat out of that? You're more than likely going to be a lot closer to the high end of that temperature range. If you are closer to that high end of the temperature range, it's as far as, let me talk this through for you. Sorry. The slower the air goes, the more time it has to absorb the heat off the heat exchanger, and the hotter the air comes out. The faster it goes, the cooler the air comes out because it's moving across the heat exchanger faster. So you're actually on that 70 to 40 range, you're going to be closer to the 40 temperature rise than the 70 temperature rise. And what you may have to do is look at that temperature rise, make sure you're in or close to that. And if you have to finagle 25, 50 CFM to be able to balance that out, work with that number to try to get it close to where you want to be.
Next question. If you have like a multi-stage heat pump on your gas burner,
Correct.
what is your realistic on the airflow thing? Like, you want to have like 350 to 400 CFM per ton cooling.
Correct.
On heat mode, you want to be like a little bit lower than that? Is there like a same type of like rule that you can look at to do like first like low heat pump?
Correct.
Heat pump. Because like a lot of the stuff that we do, if you can set all that like to the exact CFM on the various heat furnaces, right from the thermostat, right? So like, is there a big problem that we can use
as far as as far as knowing exactly where you need to be on first stage versus second stage of the heat of the heat pump. Correct. So your heat pump, you're going to want at least 3 stages on your thermostat of heat on your thermostat. No. Okay. But a legacy system, you can do that. You typically don't even want that dual fuel, that second stage, to kick on until you're in high stage of the heat pump. You should be able to, if you're on a communicating system, you should be able to lock the dual fuel out on the first stage of heat. Lock the furnace out. First stage, correct. that should be something in a proprietary communicating system. That's not something you're going to be able to do outside of that.
Correct. I'm just saying
Yeah.
we're setting the bar system. Like with we can set our low heat CFM.
Mm-hmm.
We can set our high heat CFM, and then we can separately set.
Correct. Your gas furnace CFM is going to be the same as your high heat CFM. Yeah, that's where you're going to want to start.
But,
Yeah.
Right.
Yeah.
That's what I'm
Yeah.
trying to make
Yeah.
now, the
Yeah.
starting point, and
Yeah.
go and check our prices and make sure that everything's dialed in. But is there like a 350 to 400 CFM rule on
There isn't. It's based on your really, as far as the load, you're wanting to be wherever your manufacturer installation instructions are telling you to be with that. And there again, the slower you go, the less capacity you have. You're losing efficiency and capacity the slower you run your fan. That air has to go across that coil to design temperature to be able to pull the maximum efficiency off of it. So any other questions, come up and talk to me. I know we're out of time. I appreciate all of your time. This kind of goes over what we talked about. Thank you.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.